If we want to determine the area underneath a function between two values, the idea is to approximate the area using rectangles. So what you need to begin with is what's called a partition. Now in the partition, you take the interval a to b and you subdivide it into n equally spaced subintervals. Now this requires a set of points. So this first location is x0. Come up with a second location, x1, and then x2. Each of these is separated by the same width. Now you pick some sample point somewhere in that subinterval and you build a rectangle based on where that sample point intersects your function. So if you do this for all the subintervals, the area underneath the curve gets approximated by the areas of these individual rectangles. The height of the first rectangle is f of x1 star times delta x. Now here is this x1 star. It's called the sample point on that first interval. Then you've got the second rectangle, height times width, and there's the x2 star. So on and so forth until you get to the very final one of these rectangles. Now this can be written in sigma notation or summation notation, and here we've got some xi star times delta x. Now this type of expression here is called a Riemann sum. If we want to define the area, what we'll do is take more and more of these rectangles and make them thinner and thinner and thinner. And if we continue to refine the rectangles in this way and we come up with an answer, if we come up with a number, that number is what we define as the area. So this is the definition if this limit exists. Now remember that here we are interested in the function being a positive function on our subinterval. So what this did is it led mathematicians to define the definite integral. So the definite integral is defined according to this calculation involving the limit of a Riemann sum. In the special case that your function is positive, the result of the definite integral will represent area, but generally the definite integral doesn't necessarily connect to area.